Okay, now we have another sample problem. Actually, all the sample problem, most of the sample problem are from the textbook. So just guide you through the book actually. So I don't think it would be too difficult for you throughout the whole semester. So for this one, there are two particles, Q1 and Q2. Q1 is 8Q, Q2 is minus 2Q. So Q1 is at the origin, Q2 is at x equals capital L. At what point other than infinite far away can a proton be placed? So we want to place a proton here so that it is in equilibrium. The net force is 0 on it. Is the equilibrium point stable or unstable? This concept is a bit difficult to understand, but I try my best to explain to you. So here we have two charge. One is Q1, one is Q2. This is positive, this is negative. And we hope to put a proton in somewhere so that the net force should be 0. So there are three cases. If the proton is put between Q1 and Q2, so this one is positive, this one is positive. So the force acting on the proton should point to the right, And this one is positive, this one is negative. The force due to Q2 acting on the proton should also point to the right side. So both the force upon to the right side, they have no ways to be 0. So this one is not okay. This one is not okay. So this is not okay. So for the other case, if the proton is put at the left side, so this is positive, this is also positive, so they were repelling each other, so F1 should point to the left, and this is positive, this is negative. They were attracting each other, so F2 should point to the right side. However, there may be some ways to be 0 because the two forces are point to the opposite direction. However, Q1 is positive 8Q, Q2 is negative 2Q. So this one is stronger, this one is stronger, this one is weaker. And actually, this proton is closer to Q1 rather than Q2, which means that F1 must be larger than F2. Okay, so in this case, the net force cannot be 0. So we also reject these cases. So for the third one, likewise, the two forces are pointing to the opposite direction. And actually, this one is weaker. Q2 is weaker than Q1. However, the proton is closer to Q2 rather than Q1, which means that there may be a point, or maybe more than one, but not in this case. But there will be one point that this proton is close enough so that these two forces can have the same magnitude but in opposite direction. So we will try to calculate based on these cases. There are only 3 cases because if the proton is not on the x-axis, then the y component can never be 0. So we try to calculate based on these cases. Um, so so for F1, I think Q is, oh yeah, Q is not so important. So the value of Q is not so important. So we calculate F1. F1 is K times Q1 is AQ. AQ. The charge of the proton we denote it as QP. QP, or sometimes we just write it as small e. Small e is not 2.418. Usually in this course, E is usually refer to the elementary charge, which I will explain it sometimes later in today. So we assume the position is x. Position is x. The x coordinate for the proton is x. So the distance between the two charges are x. So we have x squared at the denominator. And we calculate F2. They have the same magnitude, but in opposite direction, so that we just keep the absolute value. Keep the absolute value. So for Q2, it is minus 2Q, but we keep the absolute value. So we write it as 2Q. And for the charge of the proton is QP. And here, it is capital L, capital L. So the distance should be x minus q, x minus L, x minus L. So we'll write it like this because the force are the same. Then we can actually cancel K, Q, QP can also be cancelled. So we multiply x squared, also x minus L squared on both sides, and then we can simplify it as 3x squared minus 8xl plus 4l squared equals 0. So this is a quadratic equation. I suppose you know how to solve it. And actually, x equals 2/3 L or 2L. So if x is equal to 2/3 L, which means that the proton is here, which means that it is not in the right hand side, because as we have argued here, the protons should place on the right side. So this one should be rejected. This one should be rejected. Because when you calculate here, this one is negative. This one is negative. X minus L is negative, but it is only a root which is not so suitable for this case. But for the second root, it is okay. We can place it at 2L. So this is the answer. This is the answer for this problem. And also it asks you whether it is stable or unstable. Equilibrium, stable or unstable. The answer is unstable. The answer is unstable. Unstable. reason is a little bit more difficult. Um, so actually, the net force. Well, well. Okay. So the net force would be K 8Q QP over A squared minus 2Q QP X minus L square, something like this. I do not switch it back because this will disappear. So we can simply factor out 2QQP, 2QQP, K. So the remaining term will be 4 over x squared minus 1 over x minus L squared. So just now we calculate the answer should be x equals 2L. X equals 2L. At that exact point, the net force will be 0. However, if we just make x to be 2L plus small delta L, so this term will become 4 over 2L plus delta L square minus 1 over 2L plus delta L minus L, which will be L plus delta L square. We just substitute this one to here, and we just ignore this one because the exact value is not really important. We only care about the side, whether it is positive or negative. So the exact value is not important, so that I just ignore this term. In this case, we can expand it, so it will become 4L squared plus 4L delta L plus delta L squared minus L squared plus 2L delta L plus delta L squared. So it's just some algebra. Then we just divide 4 by 4, so that it will become something like this: 1 over L squared plus L delta L plus delta L squared over 4 minus, this one is the same. So suppose delta L is very small, delta L should be very small, or much smaller than L, so that we usually can usually ignore the square term because it is very small. Then the square term will be very, very small. So in this case, this one is this one is larger than this one. Well, so there are two positive number, and this one should be smaller than this one, so that the inverse number, this one should be larger than this one. This one should be larger than this one, which means that this term should be larger than 0. Larger than 0. This one should be larger than 0. Which means that, suppose at this point, my net force is 0, but if I just move a little bit forward, then the net force will be positive. So, which means that there will be a force putting me more forward. And this argument will be similar if I just make it 2L minus delta L, which means that if I just go to the negative side a little bit, then the force will be smaller than 0. Then there will be a force putting me further away from this point, which means that this equilibrium point is unstable. If it is stable, which means that if I go a little bit forward, then there will be a force putting me backward. We'll go back to the original point. It's something like if we have a curvature here, and this ball placed here, then this point is an equilibrium point. If we just put it, push it this way, then it will go back. However, if you have a curvature like this can be a equilibrium point. This can be an equilibrium point. However, if there are some force putting it to the right side, then it will go through and go away. Then this one is unstable. This one is unstable. This one is stable. So maybe you learn more about this concept later, but maybe a bit difficult to understand so far, but I try to explain it like this. So far, any questions? No questions. So the remaining two sections are a bit easier. So the first one is charge is quantized. Charge is quantized. Electric charge is quantized. We check to a certain value. So the elementary charge, we usually denote it as E, which is 1.602 times 10 to minus 19 Coulomb. I usually make it 1.6 times 10 to minus 19. Just ignore this O2 at the fourth and the fourth significant digit, but it doesn't really make a huge error. So at this cost is just fine. And actually, here we say the charge is quantized. Because we have an elementary charge, we can only have n equals to integer, maybe 0 if it is a electrically neutral situation. But if it is not electrically neutral, n could only be plus or negative 1, 2, 3, 4, and so on. We cannot have 1.5 charge, 2.2 charge, something like that. So for electron, the charge is negative E for proton, positive E, neutron is 0. I suppose you have learned it in high school, the chemistry class. So here, there is a simple checkpoint. When a physical quantity such as charge can have only discrete value rather than any value, we'll say that the quantity is quantized. It is possible, for example, to find particle has no charge at all or a charge of plus 10e minus 6e, but not a particle with charge, say 3.57e. So here's a checkpoint. Sphere A has a charge minus 50e. Sphere B has charge 20e. 20e. Let me draw it. This sphere A has minus 50e. Sphere B has plus 20e. The sphere are made of conducting material, which means that the electrons are free to move and are identical in size. If the sphere then touch, what is the resulting charge on the sphere? So they touch each other, or maybe I just use a very small wire to connect them. If this wire is narrow enough, they may be ignorable, or you can just touch it. So what is the resulting charge on sphere A? Anyone can know that? The keyword here is identical in size. Identical in size, which means that after they touch each other, the charge will be equally distributed on both of the sphere. So what will be the resulting charge on sphere A? Anyone can tell me? Okay, actually, you can just add them and divide by 2. So minus 50e plus 20e divided by 2. So minus 30 divided by 2, minus 15e on both A and B. This is what I just mentioned. So so this is the answer for this checkpoint question. So another sample problem. This one is not very relevant to this chapter, but it is quite interesting. The nucleus in an iron atom has a radius about 4 times 10 to minus 15 meter, contains 26 proton. Iron 26 proton. What is the magnitude and of the repulsive force, electrostatic force between the 2 protons that are separated by this distance? So I try to make it fast because it's almost time. So so actually F is nothing but K times E square, because it asks you about the electrostatic force between 2 of the protons. So one is E, another is another E. So E square. And separate by this distance. So we just plug in all the values, x times 9 times 10 to 9 times 1.6 times 10 to minus 19 over 4 times 10 to minus 15 squared. So the force will be 14 Newton. 14 Newton. Okay, so this is easy. So the next question is, what is the magnitude of the gravitational force between those two those same two protons. So I suppose you still remember the gravitational force. Uh, Gravitational force. The form are similar. A constant times the mass of the two object and all over the square of the distance. So actually, this is 6.67 times 10 to minus 11 times 1.67 times 10 to minus 27. This is the mass of a proton all over 4 times 10 to minus 15. So the gravitational force between two protons will be just 1.2 times 10 to minus 35 Newton, which means that the electrostatic force between the two protons will be 14N. The proton will repel each other due to the positive charge. However, the gravitational force attracting them together will be just 10 to minus 35 Newton. So this is very strange. We cannot really explain why the proton and neutron are concentrated at the nucleus, and there should be something other else to really glue them together. We really need a strong nuclear force to glue the proton together. Otherwise, the nucleus cannot be stable. So actually, I will not talk about this very much, but I just show it a bit. So there's something called the standard model of elementary particle, and so it is separated into this part is called the fermion. This is the boson, and actually the proton, the neutron are actually have even smaller building blocks. There are some up quark, down quark to really construct the proton and neutron. And also we have something called the gluon to really glue the quark together. Otherwise, there are very strong electrostatic force repelling them. And actually, electron is something called the lepton. I don't really know what it really is. And actually, to find these quarks, we really need some accelerator so that the proton are collide with other particles, so that they can break up to even smaller particle. And actually, the gluon is called 高级 in Cantonese, in Chinese. So actually, there is something like a informative stuff. I don't really know much about that. Maybe some case I can just show you a bit. And okay, finally, I just go through this quickly. The charge is conserved. You cannot create a charge or eliminate a charge. We can just have something like the electron and the anti-electron, or the positive charge, so that when they add together, they will eliminate each other. There's something called the antimatter. So, and then it will eliminate something like the gamma ray. Is just physics stuff. So I just let you know a bit. And actually, the gamma ray can generate something like the electron on the positive electron, or actually it's called a positron. So this is called the electromagnetic spectrum. We will cover it more in chapter 33. So actually, just give you some idea. Gamma ray is a ray have very high frequency, which means it is a very high gamma ray is here. It has a very high frequency. The frequency is high in this direction. So we have a microwave, something like 10 to 9 gigahertz. So when we use Wi-Fi is somewhere here. So we have light, the visible light, which are here, and the gamma ray is something have very high energy. And X-ray is a bit lower energy, ultraviolet here. So you may know that the frequency of the proton of the photon relate to the energy it has.